So I guess we can start for the next session. Okay.
Okay.
Yeah.
So welcome back. Before we stopped for the break, we talked about simplex. So remember, this is this very well-established algorithm for solving linear programs. And we saw one example of how we can use it to solve a set of linear constraints. But now we want to move and see how you can also handle ReLUs, right? How you can verify a neural network that also has the activation functions, which are the interesting component, really. So we now want to move from simplex to ReLUplex. Okay, so each rel remember in our neural network we have these ReLUs, right? We have ReLU nodes, and we're going to take each of these ReLU constraints and we're going to represent them as a pair of variables. So we're going to use a variable xw to represent the weighted sum going into x, right? So this is the input to the ReLU. We're going to use another variable called xa to represent the output, the activation result. So the ReLU constraint will be represented by two variables, not just one for the input, one for the output. And the one key point is that we are going to allow these two variables to change independently. So we're not going to enforce the ReLU constraint all the time, but rather we're going to let these two variables change independently. We're going to allow them to change the ReLU constraint, to violate the ReLU constraint. Right? So similar to how simplex allows variables to be out of bounds temporarily. And we're going to fix these problems as we go, iteratively, incrementally. And the two operations that we will use are just the same two operations that we had before. Okay, so still pivots and updates. So this doesn't change. So we're going back to the same example, only now we assume also that we have ReLUs. Okay, so from now on, we have again the ReLU constraints applied to x2 and x3. So when we encode the problem, we now have two variables that represent the first ReLU. So x2w is the input and x2a is the output. And likewise for ReLU of x3, we have x3w and x3a to represent the input and output to that ReLU. So now our neural network is slightly larger. And we again encode this neural network using weighted sums and bounds. Okay, so very similar to before. So for each weighted sum, we have an equation. So now we use the w variables and the a variables were appropriate according to the topology. And the bounds are, again, very similar to before, right? So x1, we know is between 0 and 1, and x4 is between 1/2 and 1. This is the property that we're checking. x2 and x3w, right? So these two are unbounded. Weighted sums can be positive or negative. We don't care. And the activation results, x2a and x3a, we know they're non-negative. This is by definition of a ReLU, right? The output of a ReLU can never be negative. And the auxiliary variables 5, 6, and 7, sorry, are just 0, same as before. So now, again, I'm not going to give you the exact algorithm. I'm just going to show you an example, and hopefully it will convey the meaning. So we again have all of our variables and the current assignment. The assignment, again, we will make sure always satisfies the equations. We have lower bounds and upper bounds for the bounded variables. And now, remember that these two variables, the x2a and x2w variables are a ReLU pair, and x3w and x3a are also a ReLU pair. So this we remember, right? We know that they are a pair. So in the first iteration, very similar to before, x4 is too small. Right? It's a right-hand side variable. It's non-basic, so you can just do an update step. So we do an update, and x4 increases. Consequently, x7 also increased because it depends on x4. The second iteration, x7 is too great. We do a pivot step, and we do an update step. So this is the same as before, so I'm rushing through this. And then once x7 has become non-basic, we can do an update and reduce its value to 0. And now comes the interesting point. So if you look at the assignment now, you will see that all of the variables are between their bounds. Nobody is too small, nobody is too great. You will also see that the equations are satisfied because this is an invariant. We always make sure that the equations hold. But now we have a ReLU problem. Right? So this is the input to a ReLU, and this is the output to a ReLU, and they don't satisfy the ReLU constraint. Right? Because the input is 0 and the output is 1/2. This doesn't make any sense. So what do? Same thing that we always do. We pick one of the variables, in this case x2w, and we say you are too small. If you were to be 1/2, then we would be good. So let's increase. Right, so x2w is non-basic. So we just apply the update operation, and we increase its value to 1/2. Now, as before, because we touch x2w, we also change x5, because we always want the equations to hold. But the point here is that the motivation for this update step is because of the broken ReLU constraint. And once we do the update step, this ReLU constraint has been satisfied. And even more importantly, we didn't do a case split. Okay, we didn't guess in advance that x2 was going to be active or inactive, but rather we fixed its value on the fly in order to make it satisfied. So this is precisely what we mean by lazy splitting. Okay, you don't start with a split and then solve the problem, but instead you try to find an assignment that solves the problem while avoiding the splits. So now after this iteration, x2 is in good shape, but now x5 is too great, right? It should be 0, but it's 1/2. So we go back to the core simplex, right? So x5 is too great, you do a pivot, you do an update. And then this is actually the point where we got stuck before, right? So x6 is 1/2 and should be at least, at most, a 0. But now there is a way to solve this. You can do a pivot with x3w. This time there is no, we don't get stuck. And finally, you do an update step, and x6 is decreased, which leads to this assignment. And at this point, we get a success notice. So if you look at everything that you have, all the equations are always satisfied, so that's not an issue. All of the variables are between their lower and upper bounds, so nobody is out of bounds. x2, right, so this ReLU pair, the ReLU is active and satisfied, so the input is 1/2, the output is 1/2, that's good. ReLU number 3, the input is negative and the output is 0. Right, so it's in the inactive phase, but that's also okay. As long as it's satisfied, that's fine. So both of our ReLUs are happy, and so all of our constraints are satisfied. Equations, bounds, and ReLUs. And what this means is that the assignment that we found is the counterexample. That's the satisfying assignment. And indeed, if we take the neural network that we started with and we assign the values that we got, we see that everything is satisfied. Right? So the input is between 0 and 1, the output is between 1/2 and 1, and all of the ReLU constraints along the way are satisfied. Okay, so I really hope that this conveys to you the intuition behind ReLUplex. Of course, you need to formally define the algorithm, and that you can see in the paper, but I hope the intuition comes across. Does anybody have any questions? No. Okay. So now let's talk a little bit about the properties of this algorithm. So much like simplex, the algorithm is sound and complete with a little star. So soundness again means that if the assignment, if you get SAT, then the assignment is correct. If the assignment is unsat, then you know, if the solution is unsat, then you know that there is no satisfying assignment. And as for completeness, well, this again depends on a couple of things. So just like simplex, right, it depends on the variable selection strategy. Because in particular, you can have just simplex problem and solve them with ReLUplex. You need to have a variable selection strategy that guarantees termination. And also you need a splitting strategy. So why is this the case? Because you can have a situation where you have, say, a variable that is violating a ReLU constraint and you fix it. And then because of the fix, you have another variable that is now violating a bound. So you fix that constraint, but now it again violates the original ReLU constraint. So you can have this little fight between a ReLU constraint and a bound constraint. And when you fix one, you break the other and vice versa. So in order to guarantee termination in those situations, you will eventually have to do a case split. Okay, so in some cases, there is no way around doing case splits between doing a split in your tree and going to the next layer. So you may need to do this, but the idea is to do this very, very lazily. So if you want to ensure termination, you need to eventually guarantee that you will split. Okay, so one naive approach that guarantees termination is just the eager approach. It says split on all the variables immediately. Right, so very eagerly take all of your values and for each of them do a split. Right, so this is like guessing that all of them are active or all of them are inactive, etc. And once you do that, you have effectively returned to a simplex problem, to a linear problem, and then you solve it using simplex. So this is the naive approach. This is the eager case splitting, but this is not useful in practice, but this does guarantee termination. A more efficient technique for doing this is, again, in the spirit of lazy splitting, is to start by fixing just the bound violations, not the ReLUs, not doing a case split, sorry. Once all the variables are within the bounds, then you start fixing broken ReLUs, like we saw in the example. If a ReLU is repeatedly broken, that is, if you find that you are constantly fixing the same ReLU again and again and again, then you say, okay, this must be a problematic ReLU, so I'm going to split on it. This ReLU, I cannot solve the problem as long as this constraint is present, so I will do a case split, and I will transform it into a linear constraint. And this makes the problem simpler, and then you can hopefully solve it. And then you repeat this as needed, and this will guarantee termination in the end. And what you get in the end is that you end up splitting on just a fraction of the ReLUs. Right? So even just by doing this, by very lazily splitting on ReLUs instead of eagerly, you reduce the number of splits that you do very, very significantly. Okay, so this means that your depth in your search tree is 20% of the original, which means that instead of doing 2 to the power of 300 splits, you're doing 2 to the power of 60, which is a huge, huge difference. So this is the intuition of lazy splitting, and that's really, really very important if you want scalability. And it's very similar to what you do in SAT and SMT, right? So this is a very common technique. Another thing that happens a lot in SAT and SMT solvers is deductions, right? So I'm sure you have talked about implications and implication graphs and all of that stuff. So what is the equivalent in verification of neural networks, right? What can you learn as part of the search procedure that will allow you to curtail the search space? So the facts that we are looking for are what we call bound tightening. So as I'm sure you've seen in the small example that we went through, you are when you do simplex or reluplex, you repeatedly encounter equations. And equations you can use for bound tightening. What does that mean? So for example, if you have, suppose these are your current bounds that you know. So you know that x is at least -2 and y and z are each at least 1. And now you come across this equation as part of your simplex operation or reluplex operation. From this equation, you can actually deduce a tighter bound. Okay, so you can actually deduce that based on what you know now, x should be at least 2, right, which is a tighter bound. So instead of -2, you get 2, which is much better. Why is this better? Because if x is part of a ReLU pair, right, if it's either the input or the output to a ReLU constraint, then you know that that ReLU has to be in its active phase. You know that that ReLU is fixed. And this is really what you're looking for, right? Because remember, also from the NP completeness proof that we saw, the cause for the complexity of this problem is the presence of ReLUs. Every ReLU that you can get rid of makes your program makes your problem smaller, makes it closer to a linear program. It makes its complexity smaller. And so if you can derive a bound, right, if you can learn a new fact that will allow you to eliminate a ReLU, that's really, really useful. And it's definitely worth it spending your time deducing these facts. So this is bound tightening. So one way to do it is by looking at equations. There are other techniques that you can use for bound tightening. And once you have this bound tightening, this connects to one of the questions that we had before. You can store these things as an implication graph. Right? You can say that because z was at least 1 and y was at least 1, and you have this equation, then this causes this tighter bound. So this is a fact that you are able to deduce from these earlier facts. So you can store this as an implication graph and then use this information when you hit a conflict and you want to decide where you want to backjump to and how many facts you need to, how many decisions you need to undo from your stack. Does anybody have any questions on this? Okay.
So the 20% that you said, which are the ReLUs that need to be split finally, is that after bound tightening or before bound?
So that was with bound tightening, but with a very trivial or, well, not trivial, but simple conflict analysis. So there are very, we didn't have the full-blown conflict analysis in reluplex because storing these things efficiently is tricky because you have many, many of them and you need to think about how to store them a little more efficiently. And this is something that we are actually just now adding to Marabou, so the follow-up tool. But the 20% that you saw are with a very basic conflict analysis, yes.
Oh.
Okay, so like I said, in simplex and reluplex, at every step, right, every time you do a pivot, you have an equation. It's typically an equation that you didn't have before. So you can use that equation for bound tightening. Actually, you can do it for all the variables, right? So if you have x equals y plus z, then you can just as well tighten bounds for y and z, not just for x. And you can do this quite efficiently. Okay, so this is a very cheap bound tightening operation that you can do. And it's particularly useful to do this after splitting. Right? So if you just did a case split, you have deduced a tighter bound for for one of your value constraints. Because of the k-split, you can use bound tightening to propagate this fact to other variables as well. So many times when you do a k-split on one variable, the bound tightening will make it so that you're able to deduce the phases of other variables as well. So this is useful to do, and of course you can combine it with back jumping. And I won't talk about back jumping because I'm sure we've covered this with Armin. So what are some of the other things that you can do? Right, so we want to improve even further. So one of the things that obviously everybody is doing is engineering, right? So we know this also from SAT solvers. Sometimes engineering tricks can have a huge impact on performance. So this is something that people are doing. We are also doing this as part of the marabou procedure tool, just doing engineering improvements. Another very interesting thing is parallelism. Okay, so this is something that is quite difficult, right? It's an open problem, I would say, also for SAT and SMT solvers. How do you efficiently parallelize solvers? And in the verification of neural network, what we have seen to be fairly efficient is actually to do a splitting of the input space. Right? So if you have, right, if this is your input space and this is maybe your precondition P, then what you are typically doing is trying to find a way to split not the neural network necessarily, but rather the input space, right, into P1 and P2, such that verifying P1 and P2 separately will be much cheaper than verifying P at once. And when can this happen? If you are doing the partition, this partition between P1 and P2 in a way that guarantees that for P1, many of your values get fixed into one phase, and for P2, also many values get fixed into one phase. Right, so what this can happen is that it can make your search tree much shallower on both sides. Right, so P1 will be much simpler to solve than P because it will have many fewer values, and likewise P2 will also be much simpler than P. Right, and if you can make this partition in an intelligent way, this has been observed to be a very efficient parallelism approach. So of course, there is a lot of heuristics going on, right? So you need to find good heuristics for doing this, but this is a very promising and interesting direction for parallelism. And another thing that people have been up to, including us, is what we call network level reasoning. So one of the difficulties in ReLUplex, as I've shown it to you now, is that you only regard individual constraints, right? It doesn't have any intuition of the neural network as a whole. It doesn't know about layers or the stuff or the like. So there are techniques, some of them I mentioned when I talked about related work, that do make some use of the topology of the neural network. And you can use them also as a deduction engine within your solver. Again, typically what we use these techniques for is deducing tighter bounds. And you can occasionally run them to see if you can learn new facts and then integrate them into your search procedure. So this is also something that we have been up to. So this is the marabou project that is currently very active, and like I said, available on GitHub if you want to play with it. Okay, so we talked about simplex in this part of the presentation. We saw that it was a very efficient technique for solving linear programs. And then we saw how it could be extended into ReLUplex so that it can also handle ReLUs. We talked a little bit about some highlights for efficient implementation. And up next, I want to tell you about the use cases where ReLUplex was applied. So we're starting to talk more a little bit about applications of how you can use it. And there's actually another presentation that I will go to after the next break, where we will talk even again on additional applications. But right now, I want to tell you a little bit about the ACAS-XU example and what was the end of the story there, and also about adversarial robustness. Any questions before I continue?
Hi. If we don't use case splitting, is there any guarantee that ReLUplex will stop?
No, so I can actually guarantee that it won't stop, right? So for every interesting example, so in the toy example that I showed you in the slides, we didn't do any case splitting, right? We were able to find an example without any case splitting at all. But in practice, if you have a real neural network, all the examples that I have ever played with, you have to do case splitting. You cannot, unless it's a very, very trivial case, you won't be able to find a solution without case splitting.
Can you comment on for how many neurons the phase is fixed versus you have to solve using case splitting?
So the rule of thumb number that I gave, at least for the ACAS-XU networks, was about 80% of them. Well, it's a little tricky, right? But let's say the depth of the tree for the ACAS-XU networks, there are 300 ReLUs. So in the worst case, your tree will have depth 300.
Yeah.
Our average results were that the depth was about 50 or 60 at the maximum depth. Okay, so this is about 20%, 25% of the depth that you need to cover. And even then, this is not a full tree, right? So it's not like you have a full tree of depth 50. You have many of the branches of the tree are also curtailed. So I would say maybe even 15% of the number of states that you need to do in the worst case. But this really differs from one network to the other, one property to the other, and it depends on the deduction engines that you use. If you have clever deductions, then you will curtail it even further.
Yeah.
There's a question in the chat. How do you decide at 1.2K split and which ReLU do you split on? So this is where it comes to heuristics, right? So there are many heuristics that have been proposed. The heuristics that we used in the original ReLUplex was as follows. For each ReLU, we count how many times we did a fix on, right? So suppose maybe you have like ReLU 1, ReLU 2, ReLU 3, right? And for each of them you count. So you say, okay, now ReLU 1 was broken and I had to fix it. Now ReLU 2 was broken. Now ReLU 1 was broken again and again and again. And then once the count hits a certain value, you say, okay, ReLU number 1 is problematic. I keep having to repair it again and again. So I'm going to do a split on this ReLU. Right, so your first split in the tree is on this ReLU 1. You say ReLU 1 is active or ReLU 1 is inactive. Right, and this is your first split. And then you ignore it. You don't need to care about it anymore. And then you start again, right? And now maybe ReLU 2 is now problematic, so you split on that. So this is the heuristic that we used in the original ReLUplex algorithm. And really, you can separate this, right? You can say, when do I split? So this is one question, and you can use one heuristic for that. And then you can have, the other heuristic will be for, okay, now that I know that I need to split, who do I split on? And people have proposed splitting on ReLUs that are in the earlier layers versus ReLUs in the later layers. Or say, if you have a ReLU who, like, you can ask, what are my current bounds for the ReLU? And so if I have one ReLU that the bounds are currently between -5 and 5, then this is what we call a well-balanced ReLU. Right? It can either be in the active phase or the inactive phase equally, according to its range. Whereas if you have another ReLU that is maybe -0.001 and a million, you say, okay, this ReLU is almost guaranteed to be active. Okay, so you can think about splitting on these ReLUs or splitting about these ReLUs. And there are really all kinds of heuristics. And as is often the case with heuristics, we really don't know. Some of them are more promising than others, but this is really, it really depends on the problem that you want to solve. And you can do a portfolio approach, try different heuristics for your particular problem. Any other questions? Okay. So let's get back to the ACAS-XU system. So this is just to remind you what that system was. So remember the drones and the anti-collision system thingy where it needs to tell you if you turn left or right. So the FAA implemented this system using a family of 45 deep neural networks. And what they wanted to prove for these networks was that the alerting regions are consistent, right? So the network doesn't switch between advisories when it doesn't have to. They also wanted to show that there are no unnecessary turning advisories. So unless there is really a need to turn, the network shouldn't tell you to turn. And they also cared about not having strong alerts when you don't need to, okay? Because doing a strong turn to the right or to the left is considered very undesirable. So they really care about not having these alerts when you don't need them. So the FAA was able to define some of these properties formally. So the FAA experts sat down and they said, look, here are a list of 10 properties that we really care about. And these are, again, given as constraints on inputs and outputs, linear constraints. Okay, so many, like I said, many interesting problems fit into this mold of linear constraints on inputs and outputs, in particular, also in this case. And they gave us a list of 10 properties. For example, if the intruder is near and approaching from the left, and then the network advises strong right. And this they formally defined, okay? So they gave this as linear constraints on the inputs and outputs of the network. And in one case, like for example, for this property, we were able to prove it. So again, prove it for any possible input that satisfies these preconditions. Right? So a much stronger statement than just, look, we tested and it seems to be okay, but rather a much stronger guarantee. In another case, they had another one of these properties where they wanted to make sure that the alerting regions were consistent. And here we were actually able to find a counterexample. Okay, so we actually came back with a concrete input for which the network gave an incorrect classification. Was there a question? Okay, so this, when you do verification officially, your goal is to prove that systems are correct. But what you really want to do is find bugs, right? So, we were happy to find a counterexample here. Yes, please.
Yeah. So when you, for such safety critical systems, when you show that something is unsat, I guess you also give a proof, right? Some DRAT or something, I don't know.
Right. So proof production is okay. So that's a good point, right? So if you have a counterexample, you just give it and the user can check. If you say unsat, then there is a problem, right? Because either the problem is really unsat, or somebody might be concerned that your tool has a bug in it. So SAT solvers, can produce proofs. Many of them, sometimes SMT solvers can also produce proofs. So far, we don't have, I think, any tool for neural network verification that is proof producing. This is something that we are working on for Marabou right now with one of my students. There is a question of, the tricky part is all of the deductions, right? So we have a lot of clever deductions, and if you have a proof certificate that you are giving back, then you need to account for them. You need to somehow express them in the proof. And this is the research question there, apart from engineering, right? You also need to instrument everything to produce proofs. So this is a very interesting problem, and we're working on it.
Thanks.
Any other comments or questions? Okay, so let's continue. So this is just the list. You can find in the paper the formal definition of all the properties and the exact statistics that we had. Just for the question that we had before about stack depth, right? So stack is the maximal stack depth is, I'm not sure if this was the maximal or the average. I think it was the maximal. So what you get here is like how deep your search tree was at its deepest point. So you can say that this is much more shallow than the 300, which is the maximal value that you could reach. So there is a lot of advantages to lazy splitting and even simple deductions. I want to tell you a little bit also about adversarial robustness, right? So remember, this is the thing with the pandas and the gibbons, where slight input perturbations cause your neural network to go crazy. And this is really something that machine learning folks are struggling with. So this is a very, very hot topic in machine learning. So you can use verification to prove that your network is robust to adversarial examples. Right, so the verification query is given a panda, right? So given a particular input point x0 and a given amount of noise delta, does the classification always remain the same? And we already saw that you can express this as a verification query. Right, and there is here something that you need to consider is what is the definition of distance, right? How do you measure the 2 points are near? So the easiest norm for us to work with is L infinity because it translates into linear constraints. You can also work with L1 norm, right? Because this is a piecewise linear constraint. So you can always also express that one, for example, in duplex. But in general, right, if assuming you use a distance of a norm, like a definition of distance that you can support in your verification engine, then you can express these queries as well. And then you can actually find the optimal delta for which your network is robust, right? So you can do binary search and find the smallest delta, right? So the minimal amount of noise that your network, that using that amount of noise, an adversary can fool your network. So this really gives you a strong guarantee on the minimal amount of noise required, and you know that anything below that level, your network will not be fooled. So here is one example. Okay, so we took 5 examples. We took one of the ACAS-XU networks. And we took 5 input points. So each row in this table is one particular input point. And the columns of the table are the amount of noise that an adversary is allowed to use in L infinity norm. And you can see, for example, point number 2, right? Even for the highest amount of noise that we allowed, we got unsat, right? So the point is robust. The network is robust around that point. Even if an adversary is allowed to add this amount of noise, which we consider to be a lot, then the network is robust. On the other hand, for point number 1, you can see that the optimal delta is somewhere between this amount and this amount. Right, so here the network was unsat, the query was unsat, so the network could not be fooled. But once you increase the amount of noise, then suddenly an adversarial example exists. So the optimal delta is somewhere between these two values, and you can continue with binary search to find it up to the precision that you care about. Okay, so this really lets you assess the robustness of your neural network at various points, even against attacks that you don't know yet. Any questions?
How well attacks are usually able to do on these benchmarks?
How well the attacks are doing?
Yeah.
So that's an excellent question. It's the next slide. So assessing attacks and defenses. So you can actually use verification to assess attacks, right? So if somebody comes and they say, look, I have this amazing attack, and it performs better maybe than attacks that were previously known, using verification, you can compare it to the ground truth, right? You can find the optimal solution to the problem and compare the attack to it, and then you can get some sense of how good the attack is. Right, so you can pick a point X, use verification to find the optimal delta, use the attack to find delta prime, and then ask how delta prime is close, how close delta prime is to delta. And here we did some evaluations. And for example, we took the Carlini-Wagner attack on some small MNIST networks. MNIST is a family of problems of digit recognition that people use a lot. And we saw, for example, that the Carlini-Wagner attack was pretty good, right? So on average, the deltas that it could find were only about 6% smaller. I'm sorry, the deltas that the attack found were approximately 6% smaller than the ground truth. Right, so on average, the attack was doing pretty well, although there were a lot of outliers where the attack performed very poorly. Right, so this gives you a sense of which attacks are doing better on average.
So a quick question on this. We use verification to find optimal delta for which where it is robust, right? And then we try to find delta prime for which the attack is possible. Okay, I'm just trying to make sure if I understand correctly.
Yeah, so this is, okay, so this delta is the minimal delta for which you can find an adversarial example. So any amount of noise below delta, the network is robust. Delta is the first time that you can fool the network. Does this make sense?
So do you mean that verification can do better than the attack here?
Yeah, verification finds the optimal solution. Right, so you can think about it like this. You start at some point, right, and you know that if you allow a huge amount, well, my drawing is poor, but if you allow an infinite amount of noise, right, maybe this is a panda. If you allow an infinite amount of noise, then you can just change it into a cat, and the network will say cat, and that's fine. So you know that if you allow an infinite amount of noise, you can fool the network. And then you start doing verification query. You ask, okay, right, if I allow this amount of noise, can I fool the network? If I allow this amount of noise, can I fool the network? If I allow this amount of noise? And eventually you find the flipping point where it goes from SAT to unsat. Right? And then you can do binary search and you can find the minimal delta, right, which is maybe this one. This is your delta. This is the first time up to your desired precision when you were able to find a counterexample. And you can prove using verification that anything below this delta, there is no counterexample. So in a way, verification is the optimal attack, right? It finds for you the smallest amount of noise with which you can fool the neural network. And once you find this delta, you say, okay, now let's run the Carlini-Wagner attack, right, and see the delta prime that it finds. And we know that certainly delta prime will be at least as large as delta. And then you ask, what is the ratio, right? How much is this? How much better did the verification do versus the attack? Does this make sense?
Yeah, thanks. Yeah.
Okay, so just like you assess attacks, you can also assess defenses.
I have
sorry?
one. Yeah. So what you've shown just now is talking about delta in a certain global sense, right? It's like looking at all pixels of the image and saying how much deviation from there.
So it's
It-
all the pixels, but for a particular input point.
yeah,
Hmm?
for a particular image,
Yep.
considering all pixels, right?
Right.
So
Yes.
is there a way to kind of find this out? I mean, maybe some part of the image is really the most sensitive part, and if you
Right. So that's another excellent question. So this is related to the question of explainability a lot, right? So sometimes when you have a neural network, you want to explain why it makes a decision. So for example, you could say, look, here is an image of the dog, and the neural network said that it was a dog. I want to understand why. And then people are starting to ask, okay, which of the pixels are more important? Right? Which are the pixels that because of their values, it was determined that this is a dog, and which are the pixels that could have other values, but for those the neural network doesn't care, right? It would still say a dog. So your question, you can ask these questions also. You can use a verification engine to solve them. And usually the application is explainability, right? You're trying to identify sets of pixels that are more, have a stronger role in the classification that the neural network outputs. So it's a very active field of research, and yeah, an excellent question.
thanks. Yeah.
Okay. So just like you assess attacks, you can also assess defenses. And how would you assess a defense? Well, you start with a network N, and you train a hardened network N bar. Right? So this is what the defenders are doing. They are coming up with techniques for retraining your neural network to make it more robust. So you start with the original network, then you harden it. Now you have two networks, and then you pick a point, and you use verification to measure the optimal delta before and after the hardening. And this gives you a sense of how much the hardening contributed. And here we took a defense that was proposed in 2018, again on a small MNIST network, and we saw that on average, it pushed the optimal delta away by over a factor of 4. Right, so if previously I needed X amount of noise to fool the network, now on average I need more than 4X. Right, so I need a lot more noise. So on average, this defense that we checked was very useful. Right, so it really pushed away the adversarial attacks significantly. Although it is interesting to note that in some cases, it actually made matters worse. Right, so on average, the defense does well, but there were cases in which after the defense, the adversarial attacks were actually closer. Right, so we needed a smaller amount of noise in order to fool your neural network. So lots of interesting things that you can do with verification, also with attacks and defenses. Now, before we finish this part, I will very quickly talk about global robustness, right? So sometimes people are worried and they say, okay, well, that's very nice. You measure the robustness for a particular input point, so for one panda, but your input space is huge, right? So what does it say about other points in your input space? And also, what is an acceptable delta, right? What is an acceptable amount of noise? So what we do, there is another variant called global robustness, in which right? So for example, if you have X1, right, which is a point that is deep inside a region, inside the weak right region, then we expect a very high level of robustness for X1. Because even if the input is slightly to the right or slightly to the left, it is still in this green zone. X2 is on the natural boundary between two labels. So here maybe we can accept even a very small level of robustness, right? Because if you go right, then you are clear of conflict. If you go left, you are weak right. So it is acceptable to have a very low level of robustness there. So all of these things you can also tackle, and you can solve them using what we call global robustness. And here, instead of looking at the classification that the network outputs, you look at its level of confidence. Right? Remember, when the network says panda, it said, remember from the example, it said panda with 57% confidence, or gibbon with 99% confidence. So these confidence levels are just the outputs, and these are the values that the network assigns to the outputs in the output layer. So what you can ask, instead of saying, right, if I add a slight perturbation, can the classification change? You can ask, if I add a slight perturbation, will the confidence level change a lot? And if you think about this, this captures also the case where you have a point that is on the boundary, right? Because here the confidence levels for weak right and clear of conflict will be about 50% each. So if you change a little bit, then it's okay. You know, one becomes greater than the other, but they don't change by much. Maybe it will be 51 versus 49. That's fine. As long as you don't have a case where you go, from 2080 to 4060, right, where there is a dramatic spike in the level of confidence. So this is something that you can capture using this global robustness, which is also something that you can use verification to prove. But we're almost at the break, so I don't want to talk more about this. I will say one more thing. So there was a question before, how do you pick delta? Right? What kind of values do you use? Do you need to have a human expert in the loop? So in general, you do, but there is a technique that I proposed with colleagues on using clustering. And in clustering, what you do is you sort of look at various points for which you know the answer. Maybe this is your training set, right? So this is a network that needs to classify between circles and stars. So you look at all your training set and you identify clusters of circles and clusters of stars. And you say, okay, in this cluster of circles, I expect everything to be a circle. And in this cluster of stars, I expect everything to be a star. So this is fully automatic, right? You can identify the clusters and check that the network is robust inside the clusters automatically. And then when you find a counterexample, only then do you show it to the human expert and have them say if this is truly a counterexample or not. So this is one step towards automating this process, but this is really a very interesting open problem. So this brings us to the summary of this part of the slides. Why don't I quickly rush through the remaining slides and then we can go on a break, and then when we return, we can talk more about applications. So we know that machine learning today is becoming widespread and it is increasingly being used in critical applications. So it's very important to verify. And the two main questions that we are trying to solve are how do we verify? Right? So we need scalable verification approaches. And also, what do we verify? So we mostly talked about this in this slide, in this presentation. And when we return from the break, we will talk a little bit more about what to verify, how to apply this technology. And when we talked about the approaches that people have proposed, we saw the sound and complete approaches, which are trying to solve an NP-complete problem and usually do this using case splitting. And we saw that they can be improved with deduction steps and splitting heuristics and local optimization steps. And we also saw some, or briefly mentioned, some of the approaches that trade away completeness in order to get better scalability. So we talked about DLV and the discretization approach, and there's also correct by construction networks and other stuff that we didn't talk about. And as for properties to verify, well, this we will talk about after the break, so I will skip also this slide. And I will also, and I briefly mentioned that we have this project called Marabou, which is an improvement of ReluPlex, in which we are working on improving the scalability of the approach in various axes that I won't go into now. And we also actually talked a little bit about proof certificates, which is something that we are trying to implement also. Okay, and I think that we can stop here. So let's take the 30-minute break, and then when we return, we can talk a little bit more about applications.
Thank you. I think so. All of us will move to Discord, and you can, just like the last 2 days, you can join a voice channel to chat more, ask questions.